Welcome, everyone. First of all, I would like to thank the organizers for giving me opportunity to present this work. And today I'm going to talk about HighSpeedAllSkyMonitor for fast radio bursts and Technosignatures. And this work has mainly been done with my colleagues from Curtin University, Danny Price and Randall White, but also other people from Curtin contributed to some particular parts published, which have already been published, especially Ramesh Bhatt and Jess Broderick, and other people from Curtin obviously work on the SKA-Low stations, and this is also in a context of wider collaboration, SKA-Low collaboration. So I will start with a bit of an introduction what fast radio bursts are, or FRBs, and as many of you know, they are millisecond radio pulses, and the first fast radio burst was discovered in 2007 by Lorimer in the archive data from Parkes telescope. The so-called dynamic spectrum of this FRB is shown in the image on the right, where you can see intensity as a function of frequency and time, and also what you can see there that the pulse arrives earlier at higher frequencies than at low frequencies. The pulse is shown here as this characteristic dispersive sweep. So the time difference between arrival at high and low frequency is given by this equation at the bottom, and it's proportional to dm. dm is the dispersion measure, and this is an integral of the electron density along the line of sign between us and the FRB. So as you can see, they were discovered quite recently, so not surprisingly, they still require full physical explanation, and they are still quite relatively unknown objects. So in the recent years, several of these events were localized, and their host galaxies were localized. So these are allowed to measure redshift and establish that they are of extragalactic origin, and therefore it implied huge energies of the order of 10 to the 39 ergs, and hence require coherent emission mechanism. Now we know that some of FRBs are known to repeat. Many people believe that some people believe that all FRBs repeat. It is just a matter of the sensitivity of the telescope that we don't really observe all the repeats. So initially, as I said earlier, first FRBs were detected by Parkes radio telescope, and then ASCAP started to detect FRBs and detected many of them. Arecibo detected first repeater TINC FRB, 121102 FRB, and then Atmos, refurbished Atmos, started to detect FRBs at frequency of 830 megahertz. I should have mentioned that Parkes and ASCAP both detected these first FRBs were detected around 1.5 gigahertz. In the last years, Chime telescope, radio telescope in Canada, started to detect many FRBs. In fact, it can be called an FRB factory. It detected hundreds of FRBs and between 400 and 800 megahertz. And what I would like to point out is that up until very recently, basically last year, there were no FRB detections below 350 megahertz. However, last year we did have at least first publications about these detections. So the one FRB was detected by Green Bank Telescope, GBT, at 350 megahertz. This is the image shown on the left. This is FRB. This was FRB 200125A. Not a very bright one, I must say, quite a weak source. And then we also had detections of repeating FRB 180916B down to 110 megahertz frequency by LOFAR. So this, as I said, is repeating FRB. So what you see on the right are dynamic spectra from this FRB of many pulses that were detected by LOFAR. Interestingly, LOFAR observed simultaneously with high-frequency radio telescope Aperture, and I think other telescopes as well, possibly CHIME. And in most cases, low-frequency emission and high-frequency emission were not observed at the same time, so they were observed at different times. And this repeating FRB was also detected by other radio telescopes now, for example, Sardinia radio telescope, and I think several others. So last year, we also had an interesting detection of radio pulses from galactic magnetar, SGR 1925+21. So I would like to first mention that magnetars are highly neutral, highly magnetized neutron star, where magnetic fields are of the order of 10 to the 14th, 10 to the 15th Gauss, and they have been so far one of the main candidates for FRB progenitors. I will come back to this in the next slide, I think. So this magnetar, and they also over years they were often observed in X-rays and gamma rays by detectors on board satellites, and in this case it was similar, but besides this there was a radio signal detected by several other telescopes, including CHIME, between 400 and 800 megahertz, with some very high flux density exceeding 100,000 Jansky. And yeah, the burst energy were of the order of 10 to the 39th X. So as you can see, still a few orders of magnitude less than typical energy of these other FRBs observed at higher frequencies. Yeah, however, this magnetar was also detected by SKA-Monitor at higher frequencies, and this with the huge flux fluence as well of the order of 1.5 mega Jansky millisecond, and burst, this energy of this burst was of the order of 10 to the 35 X, which is just 40 times fainter than the weakest extragalactic FRB. So it's not really much that is needed to actually reconcile these energies from galactic magnetar signals to other FRBs observed at higher frequencies. So it's not excluded that magnetars it's quite likely that magnetars may be progenitors, at least of some part of the FRB population. So yeah, just on the left, you see dynamic spectra again from CHIME, and on the left from this higher frequency AllSkyMonitor. As I said, these magnetars were one of the main candidates for the progenitors. Recently, actually very recently, there was an interesting glitch in this picture, because one of the FRBs, I think repeating FRB 200120E, was detected in what is in globular cluster in the galaxy M81, very nearby FRB. Interestingly, globular clusters are quite unlikely place for young neutron stars like magnetars to be. Hence, it's quite a bit of a against the theory. But on the other hand, this one was also observed by at very high time resolution, and it was shown that it has time structure on this time scales of hundreds nanoseconds, which is actually very similar to what we know can be emitted as crab-like so-called giant pulses. So giant pulses are really pulses which have huge flux, but very short duration. So of the order of tens, hundreds of nanoseconds, and they still can contribute to total fluence of the pulses. And possibly, so there was, this theory was also brought a few years back, that possibly another progenitor candidate for FRBs are giant pulses from pulsars in other galaxies. Yeah, and this is mostly, these two theories are mostly for something that would be repeating FRBs, because this would repeat every now and then. However, maybe we would not observe so many pulses because only very rarely these pulses are bright enough to be seen in our galaxy. So there is whole list of theories still with some leaders in between, obviously, but leading ones. And the one for one of FRBs, which is like just one-off event, is potentially the binary neutron star mergers, similar to what was observed as this kilonova event in 2017. But FRB was not accompanying this one at the time. It was observed as gravitational wave and also electromagnetic spectrum and also as GRB, but not as an FRB. So yeah, these are the main leading theories, but this is not my main strength. So yeah, so I was trying to detect FRBs at low frequencies, where at the time they were not detected, and for this I used the Murchison Wide Field Array, the MWA, and so in 2017 and 2010 we shadowed the same field of view as ASCAP radio telescope, and it was running its FRB survey at the time. So we were co-observing, collecting data in half-second resolution, and then we imaged this data in the same time resolution and in 1.28 megahertz channels to be able to disperse. So during this observation campaign, ASCAP detected 7 FRBs. 4 of them we couldn't really reduce the data. The data quality was not good enough because this was during daytime observations, and 3 of them were during nighttime, and this were good data. But so we knew the position from ASCAP, we knew the dispersion measure from ASCAP, so we could disperse and check that we didn't see any low frequency counterparts of these FRBs, unfortunately. So we didn't detect any. We only derived upper limit on fluence at low frequencies around 170 megahertz, which led to some interesting constraints on what is the size of the absorbing region surrounding this FRB and some propagation effects. So these are things that can be, these low frequencies can be used for. It was also shown in this LOFAR detections. So this was back in 2018. Over many years, there were many so-called blind surveys where they just observed the sky and looked for FRBs, not knowing that there was an FRB like we had with the ASCAP observations. So here in this table, which is a bit a busy one, I list some surveys, probably not all of them. In the first line, there is actually this GBT detection of FRB last year at 350 megahertz. So this one was using certain field of view of about 1/4 degree square, observed for nearly half a year with some fluence sensitivity limit of the order of 1.25 Jansky millisecond. So I constructed a figure of merit, which I assume that number of detected FRBs will be proportional to the field of view, proportional to sensitivity to the power of -3.2, which comes from the Euclidean universe, and then proportional to observing time divided by time resolution. So this is my figure of merit. Now, for this one, and then I normalize this figure of merit to my to this first survey, which actually detected FRB. So it's like a believable one. So is the only one here that detected an FRB. So some kind of a FRB rate can be derived from it. And so then I calculate how many FRBs a survey would detect over a year. So this one observed for half a year, so over a year would detect 2 FRBs. Now for the other surveys, I calculate this figure of merit and normalize it to the value of this first survey, of the figure of merit of the first survey. And this way I can sort of estimate how many FRBs would these surveys see with respect to this reference one, which actually detected 1. in half a year, or would detect maybe 2 in the whole year. So as you can see, this is the fifth column in this table. Most of these surveys have either a fraction of FRB predicted detection per year, or maybe 1 or up to 4 maybe. And most of these surveys, and this is because of the combination of not sufficiently large of field of view, not sufficiently long observing time, or not very good sensitivity. Now, in the last row of this column, I showed what this figure of merit would gives us for an all-sky monitor. And in fact, here it's not even all-sky; it's just a monitor monitoring the sky above 20 degrees elevation, which is about 12,000 square degrees. And for this one, with reasonable sensitivity of the order of 200 Jansky millisecond, it should actually detect about 140 FRBs per year, which is great. I mean, it would become another FRB factory. So that's where we are aiming to. And in fact, what is shown here, I'm not going to discuss all this equation on the right, but just comment on the picture on the left, where you can see that this system is shown as a blue curve with a very large field of view, and the other one is, and so this is like all-sky monitoring system, and we can compare it to this system of very narrow field of view but high sensitivity, and it turns out that the ratio between number of detected FRBs of these two surveys is actually proportional to the ratio of sensitivities in the power of, again, minus 3.2 for Euclidean universe, or different power law index depending on what is the index of the source count distribution of these FRBs in the universe. Yeah, so we can actually compensate for narrow field of view with for lower sensitivity with wider field of view, and we actually ran some simulations using FRB POPI by Garnier et al. And this one showed us actually that such an all-sky monitoring system may be even better than very narrow but deep surveys such as even SKA-Low. Yeah, so this is very optimistic for such an all-sky monitor, and we would like to use actually SKA-Low stations for this monitor. So as you might know, the low frequency component of the Square Kilometre Array, or SKA-Low, will be built here in Western Australia, specifically in the Murchison Radio Astronomy Observatory, or MRO. It will observe at frequencies between 50 and 350 megahertz, will be composed of 512 stations, each 256 dual polarized antennas, so altogether nearly about 130,000 antennas, and they will be distributed over an area of about nearly half kilometer square. And this large collecting area gives unprecedented sensitivity of this radio telescope. As you might also know, the higher frequencies will be handled by the South African component, and this one will observe between 350 megahertz up to 14 gigahertz. So over a couple of last years, there were a few prototype stations already constructed at the MRO, and in 2019, a new generation of stations was constructed, 2 of them. So one is shown here, is the Aperture Array Verification System 2, or AAVS2, which is 256 Scala 4.1 log periodic antennas, as the one shown in the bottom left corner here. And the second station is the Engineering Development Array 2, or EDA2, which is 256 MWA dipoles, as the one shown in the left, on the left bottom corner here. And as you might notice, they have diameter of the station is 38 meters and 35 meters for EDA2. What I would like, I will not discuss all of the details of the analog and digital signal chains, but I would like to point out that here the analog and digital signal chain allow us to digitize signals from all individual antennas and polarizations. So this happens inside the so-called tile processing units, so-called TPMs. So inside these TPMs, a firmware is runs on FPGA boards and coarse channelizes the digitized voltages into 512 coarse channels of about 0.93 megahertz and in time resolution of about 1 microsecond. And so these TPMs can send this data to the data acquisition computer. And what can be done with these complex voltages? So firstly, these complex voltages can also be coherently added inside the TPMs with appropriate time delays, such as a station beam is formed in the required direction in the sky. And this is the way the future SKA-Low telescope will operate, where the stations basically perform as low frequency dishes. And then each of them produces a stream of complex voltages in X and Y polarization, which are later cross-correlated with other stations. Now, the station beam is of the order of 3.3 degrees at 150 megahertz. This is not the mode that I will be mostly talking about. As you might notice, I am more interested in wide field observations, and these stations can also be very nicely used for this, because these complex voltages from each individual antenna can be cross-correlated to form intrastation visibilities, and this has been done in real time using XGPU software correlator, and we were producing 2-second visibilities in 2-second time resolution in just one coarse channel of the order of, as I said, 1 megahertz. And then these visibilities can be processed, and images over entire hemisphere can be formed, basically. And this is the mode that we have been using a lot, both for engineering verifications and testing, and also for trying to actually find transients. So the reason why we can actually see the entire sky is because a single antenna element in the station, which is a dipole, basically has sensitivity to entire sky, nearly entire sky. So what you can see here is the response of a single dipole over the sky, and as you can see, it has highest sensitivity at zenith, but it also has a reasonable sensitivity down to elevations near the horizon, maybe, as I said, higher than 20 degrees elevation. So this antenna patterns are for X and Y polarization, left and right, at 160 megahertz for AVS2 station. Yeah, so we've been using SUN as our both phase and flux calibrator. I'm not going into details of this. What you can see here are the actual all-sky images that we can produce with this station. So these are, I think, longer timescale images than 2 seconds. It would take too long to probably 40-second, 30-second images. And what you can see, this black stripe across the image is the galactic plane, and then sun. Now sun has risen above the horizon and is passing through the sky, and then we see galactic plane again. And yeah, these are the kind of all sky horizon to horizon images that we can produce with this station. So further, we have one of the very important tests that we have been doing over the last few years was to verify that the stations indeed perform as expected from the simulations and SKA specifications. So we have been running verifying sensitivity of the stations, and here what I show is the sensitivity in terms of effective area divided by system temperature as a function of time, and the black curve is the measured sensitivity, which actually uses all sky images as well. I may come back to this a bit later. And then the blue curve is the simulation, and as you can see, the data and the simulation agree quite well, especially at time of calibration, and especially at higher frequencies. But generally, we see that the stations perform very similar, and they satisfy SKA specifications, and so we can use for estimates of the expected sensitivity the value of the order of 2500 Jansky for the so-called system equivalent flux density, which is basically one which allows us to calculate standard deviation of the noise, expected noise in the all sky images, for example. We have also done this same. We have also done the same tests for for the EDA2 station and comparison of data and simulation, you can see in these images here. We also understand the sensitivity very well, and it compares well with the expectations of the simulation. So over these 2 years, we have collected a lot of data, and I'm now going to focus on this 2-second all-sky images data that we collected in the last 2 years. But I will mainly talk about the data collected in 2020. Often the stations observed at the same frequency, 160 megahertz, 230 megahertz, or 320 megahertz. But sometimes EDA2 would observe at lower frequency at 160 megahertz and AVS2 at higher at 230 or 320 megahertz. And typically we would collect at least 24 hours worth of data. But as you can see in this table here in the third column, some of the data sets were even 130 hours of data, so more than 5 consecutive days worth of data. And we have analyzed this data and all-sky images to look for transients, and this work has already been published. It was published in April in PASA, so if you are interested in more details, please go to and read this paper. Here is another example of all-sky image from EDA2 at 160 megahertz. These are 2-second images, consecutive images. And these are the kind of images we've been using to look for transients. You could potentially see a transient here, but it's much easier to see with human eyes when we switch quickly between both images. Or the best way for the computer is to actually subtract these 2 images and form a difference image and look for this transients here. And as you can see, it is clearly easily visible bright transient in this image. So this is the technique that we have been using. I just will mention here that also this kind of difference images were used for measuring the sensitivity of the stations using the measurement of the noise in these difference images. And the noise is in agreement with what we would expect from the simulations. So a few more examples of images as a movie, and you can see this object that I just showed image earlier is also visible here, blinking quite regularly here. So this is the technique that we have been using to find transient candidates in different images. And since we had 2 stations, we formed this, we analyzed these different images from both stations, finding transient candidates from both stations, and requiring that the transient candidates is a signal that exceeds some 5 sigma threshold. Where threshold sigma was calculated as a standard deviation of the noise in the center of the image. Then we also excluded some areas around very bright sources, for example, so-called ATEM sources and galactic center and galactic plane. And this is to exclude the artifacts of image subtraction, because during this very short time of 2 seconds, sky still rotates a little bit, and very bright sources can produce artifacts of image subtraction. Now, once we have the list of candidates from both stations, I required spatial and time coincidence of these candidates. So if the stations observe at the same frequency, the time window would be the same as integration time, 2 seconds. If they observe at different frequencies, it would be time window corresponding to dispersion delay of the object at dm of 1000 parsecs per centimeter cube, which corresponds to about 85 seconds for 160 and 230 megahertz. Now, the spatial coincidence radius was about 3.3 degrees, which is station beam size at 130 megahertz. So after this, I really had a list of transient candidates, and unfortunately, some of them would still be due to radio frequency interference or RFI, and especially at low elevations, we can see ground-based transmitters blinking on the horizon, and therefore we exclude this anything that happened at elevations below 20 degrees. We have also nearby planes passing by which can transmit, and we also have satellites, and these satellites can be quite annoying, so to speak. There are so for these satellites, every evening I would create a list of satellites in the Earth, objects in the Earth orbit. Their orbital parameters are described by two-line elements. So I would produce what I call a database, but really a huge file of 16,000, more than 16,000 objects. And for a given transient candidate, I would calculate positions of all these objects at the time of the image. And if there was any object closer than 4 degrees from my transient candidate, I would flag this candidate as potentially a satellite with the name and ID of this satellite. Now, here is an example of a satellite detection. This is specifically BGUSat, which is a CubeSat. And this, you can see the very bright transient of the order of 1700 Jański at 160 megahertz with Bob station AVS2 and TDA2 here. And what you can also see here are these false candidates marked with white circles. And these are due to instrumental effects, so-called side lobes. And therefore, when there was a super bright RFI like this one, or even brighter, then I would exclude the whole image from the analysis, because these side lobes would be present in the image, causing a lot of false positives. There is plenty of objects in the Earth orbit, and what you can see here is actually my list of my transient candidates as red dots. From the night of 10th of April last year, and you can also see some very small dots, black dots, which are basically positions of all the satellites calculated for the positions of all the images, 2-second images from this particular night. So what you can see here is basically that there is plenty out there, and it's relatively easy to think that we can match any transient candidates to some satellites, randomly match. So indeed, more than 1,000 satellites above the horizon at any given time and any distance, only about 100, 200 at low Earth orbit, which is less than 2,000 kilometers. So yeah, we can calculate the probability of false match. It saturates at 100% at around, doesn't need so much, only 240 objects. So indeed, this way is not the best to excise the satellites. We need more bandwidth, better time and frequency resolution, so that this way we can find which objects are actually the moving ones, and they could be excluded this way. So another example of BGUSat on the right, you can see my transient detections, and black curves are the orbital paths predicted for this particular satellite, which is again this BGUSat. Yeah, so we've detected many satellites. BGUSat was detected in many data sets, 7 data sets, and over a wide range of frequencies, even from FM band at around 100 megahertz and in earlier studies. And here I detected this one at 160, 230, and 320 megahertz, slightly different brightness, but generally it seems that this satellite transmits basically out of band. And some other satellites seem to be rather having a bit of spillover from their nominal frequencies, such as Triton 1, for example, observed in 4 data sets, but not at frequency which is not far from its nominal frequency. And other satellites were also observed, but just in 1 data set, more than single point. So there were many points where these satellites were detected, these objects were observed, which makes me quite confident that these are not random matches, because the probability would be very low of this kind of random matches. Now, well, as you can see, satellites are becoming quite an issue for low frequency, and not only low frequency, for radio astronomy in general. Another objects producing false positives, planes, which are tried to exclude using some predefined flight paths. But in the end, I did detect some astrophysical transients, we detected. So here you can see an example of such a detection. which is this grouping of points from the same data set. As you can see, this one was, there was a lot of transient candidates in consistently at the same position in the sky, and this turned out to be due to pulsar B0950+08. And the bright transients in 2-second image difference images you can see on the left, and the aerial difference images on the right. So you can see they are very bright, and here I constructed light curves from the both stations, EDA2 at the top, AVS2 at the bottom. And what you can see here, the transients were getting even up to 150 Jansky, which is 65 times more than the mean flux of this particular pulsar. In the beginning of the night, up to until 9 p.m., it was quiet. Then the pulsar started to be very active over the next 2 hours, and then again relatively quiet, but the noise was a bit higher. So I actually constructed a reference light curve some 10 degrees away from this pulsar, and you can see that nothing wrong is in the reference light curve, except that at the very end of the night the noise increases because galactic center rises above the horizon. So we have this triggered checking us to check all the data sets that we collected, which was about 24 data sets and over 360 hours of data. So this particular night of 10th of April last year was unusual. Over 200 pulses from this pulsar detected by both stations. Then in other nights, between 10 and 20 pulses detected on 2 other nights, but not as many and not as bright as during this particular night. So yeah, we tried to establish a little bit what it can be caused by this kind of behavior. And interestingly, similar detection was also obtained by ArtFac group, which is also AllSkyMonitor, just using low band LoFar antennas. And in the paper by Kuyak et al. 2020, they also detected this, and they claim that these are transients are due to actually something like giant pulses. I've already mentioned in context of FRBs that this pulsar basically emits giant pulses. So here I'm showing our distribution of cumulative distribution of fluence from our data. What you can see is that it's well represented by a broken power law, where the fainter pulses have a shallower slope, and the brighter pulses have slightly steeper slope. So this actually matches well the picture that it could be giant pulses indeed. And this similar power law distribution was observed by ArtFac group and other groups as well. And also this kind of behavior is seen for giant pulses observed from other pulsars, such as, for example, Crab pulsar or other pulsars. So it's a possibility. However, given our limitations in the data, we cannot firmly say that if these are giant pulses or this is due to propagation effects. So having so much data in the CAN, we actually use this data also to determine the upper limit on surface density of transients. So for this, we used two frequency channel data when ADA2 observed at 160 megahertz and AVS2 at 230 megahertz. And there were not many transients which would be seen in this data sets by both stations in coincidence. So this, except the BGUSAT, which I mentioned, and it was flagged and excluded. So it allowed us to determine the upper limit on surface density of transients brighter than 42 Jansky, which is less than 10 to the 9th transients per degree square. And this can be compared to other studies. So our point is this red arrow pointing downwards here. And yeah, it basically is consistent with other studies. It fits nicely between the ArtFac 1 second timescale and LWA, a data point from long wavelength array, or LWA, at 5 second timescale. But yeah, this is preliminary result with the quite limited sensitivity due to our limited bandwidth. So moving to our main goal, the fast radio bursts. So unfortunately, we didn't detect any fast radio bursts. unfortunately, we didn't detect any fast radio bursts. In the time of our observations, 3 FRBs were detected, 1 by ASCAP in 2019, 2 by Deeper, Wider, Faster in September last year. So we had images before, during, and after, 2-second images. We didn't detect any low frequency signals from this in the positions of these FRBs. However, this nicely shows that the power of the system. So we didn't even know about this campaign. We had images, and yeah, whenever anything goes off, such as FRB or gamma ray burst or gravitational wave event, we can have images before, during, and after such an event. And especially if we upgrade the system and have a wider bandwidth of the order of 40 megahertz, so 40 times more than now, and we go to higher time resolution imaging, we should be able to detect FRBs, and we will try to detect these FRBs ourselves. Yeah, so that's why we want to develop this HighSpeedAllSkyMonitor for fast radio bursts and Technosignatures, which we named Chase them. And it will, as I said, have 40 times larger bandwidth. We will perform 10 millisecond images, observe as much as possible, nearly 24/7, if practicable. And I have a PhD project for actually looking for FRBs in image domain using high time resolution images, looking for dispersed pulses. So, and there are other possible science goals, and especially Technosignatures. So Danny Price is particularly interested in looking for signals from extraterrestrial intelligence. So the way we are going to do this, we will have these data cubes of very high time resolution images in fine time resolution, and we will analyze basically every pixel in the image, which corresponds to specific direction in the sky. We will form dynamic spectrum for each pixel direction in the sky, like the one shown here. So you can see here detection of actual dispersed pulse, not very high signal to noise ratio, but this is crab giant pulse detected in 1 megahertz coarse channel with using the EDA2 station, using standard software for FRB searches here. So some examples of 10 millisecond images here. So that is the kind of 10 millisecond image in 1 megahertz bandwidth. But when we fine channelize, it will become really noisy, but you can still see galactic plane in this 10 millisecond fine channel image. So in the end, what we predict to see with this is based on the current rates from recent low frequency detections by LOFAR and GBT. So they predict, I can estimate based on this that the low frequency FRB is between 3 and 38 FRBs per day per sky. And as you can see, these FRB rates are highly uncertain. And one of the things that we could really do with this system is to actually establish this FRB rates very well. But given the sensitivity of the stations, these rates and minimum observing elevation, we estimate also that we should actually detect between, as I showed in the earlier table, even more than 100, maybe hundreds of FRBs per year with such an all-sky monitoring system. So to get there, we actually need to upgrade the network infrastructure a little bit. So the blue elements here are the new parts. We need to have 100 gigabit switch per station, and then at least 4 data acquisition computers which will record the data and analyze it in real time, running software on GPU cards, both for imaging and searching for dispersed pulses. We will leverage this new system with new software for fast imaging and the dispersive pulse searches. We have the expertise in the building for capturing this high time resolution data and looking for both FRBs and Technosignatures, with Danny Price being an expert for SETI searches. So there are algorithms that we can potentially use or write our own imaging algorithms, also exploring the new features of GPU, such as, for example, tensor cores. And yeah, as far as the Technosignatures go, I am not an expert on this. As I said, Danny is the main expert on this particular part. However, I would like to point out that obviously all-sky monitoring is a great thing to do, and especially if such an advanced civilization transmits a very high power signal but relatively low duty cycle every now and then it may be missed by maybe deeper radio telescope, but such an all-sky monitor should actually detect this kind of signals. So yeah, to summarize, as I said, we have used already this SKA-Low prototype station to develop first southern hemisphere all-sky monitoring system. Used it for transient searches between 50 and 350 megahertz. Interestingly, this part of parameter space, especially frequencies, is unexplored by similar all-sky monitors in northern hemisphere, which are implemented by on low-far and long wavelength array. We collected a lot of test data, analyzed this data, found some interesting activity from very long known pulsar B0950+08, but we also detected one interesting event which was further investigated as potentially an interesting object. This hasn't yet concluded. We determined upper limit on surface density of transients. Unfortunately, we didn't detect any FRBs so far, but now we are planning to increase the sensitivity of the system by 2 orders of magnitude and start to detecting FRBs ourselves and potentially Technosignatures. And this will be done by going to higher time resolution imaging of the order of 10 milliseconds and increasing the observing bandwidth by 40 times to about 40 megahertz. And other than that, if we observe 24/7, have all sky images, then whenever anything goes off in the sky, which is interesting, like kind of transient wise interesting, such as gamma ray bursts or gravitational wave event, we should have images before, during, and after such an event. So yeah, this should be very precious data. So I will stop here. Thank you very much for your attention, and I will take questions if there is still time.